Hey everyone. So imagine you're making a bunch of choices, one after another. And at every single step, you just pick the absolute best option you see right in that moment, without even worrying about the future. Well, you know that really human instinct? It actually has a pretty powerful name in computer science, and that's what we're going to break down today.
Just think about it for a second. In your everyday life, maybe in a game, in any decision you make, what if your entire strategy was just grab the best immediate win you can see? It sounds simple, right? Almost too simple. Well, this is exactly the mindset we're going to dive into.
And there it is. The official term for that strategy is a greedy algorithm. It's all about making that locally optimal choice. The best choice you can make right now, and just hoping that all those small, immediate wins add up to the best overall result. You could say its whole mantra is take the best now and don't look back.
So, here's what we've got on deck. We'll kick things off with the best now approach. Then we'll figure out when this strategy actually, works. We'll take a quick tour of problems it absolutely crushes, see it pop up in our daily lives, and then we'll ask the big question. Is this fast and simple method maybe a little flawed? Okay, first things first. Let's really break down the core logic. How does this best now thinking actually work step by step? Turns out it's incredibly straightforward. It's really as simple as it looks on screen. Just 3 steps. First, you scan all the options you have right in front of you. Second, you just pick the best one, instantly, no hesitation. And third, and this part is absolutely key, you commit, you move on, and you never ever second-guess that choice. This is exactly what makes greedy algorithms so blazing fast.
But, as you've probably guessed, this simple approach can't solve everything. I mean, if it could, things would be a lot easier. It works like magic for sure, but only for certain types of problems that have a very specific kind of structure. So let's take a look at what those conditions are.
So, for a greedy algorithm to actually guarantee the right answer, a problem needs 2 special properties. First is what's called the greedy choice property. Basically, this just means that making the best choice now won't mess things up for you later on. It's a safe move. Second, it needs optimal substructure. This sounds complicated, but it just means that the best solution to the big problem is made up of the best solutions to its smaller parts. Think of it like this. The shortest path from New York to LA has to include the shortest path from New York to Chicago, right? If a problem has both of these qualities, greedy's good to go.
So, where do we actually see these properties in action? Well, let's take a rapid-fire tour through 5 different areas where greedy algorithms are pretty much the star of the show. First up, we've got selection problems. This is all about picking items from a big list to maximize how many you can grab, while following some rules. A classic example here is the activity selection problem. Imagine you've got a list of events, all with start and end times. How do you possibly attend the maximum number of them? The greedy strategy is just brilliant. Always pick the activity that finishes the earliest. Why? Because it frees you up as soon as possible so you're ready for the next one. Next on our tour, optimization problems. Now, here, the goal isn't just about how many things you can pick. It's about maximizing or minimizing some kind of value, like profit or maybe cost. The perfect example for this is the fractional knapsack problem. You've got a bag with a weight limit and a bunch of items with different values and weights. So what's the greedy move? Simple. You figure out the value per pound for every single item, and then you just start packing the most valuable stuff first until your bag is full. So simple and so effective. All right, our third stop takes us into the world of networks and connections, what computer scientists call graph problems. Think about connecting cities with roads or computers in a big network. One of the most important tasks here is finding what's called a minimum spanning tree. It's just a way to connect every single point in a network using the least amount of stuff, like cable or roads. Famous algorithms like Kruskal's and Prim's do this greedily. They just keep adding the cheapest connection they can find that doesn't mess things up. And this idea is fundamental to how things like the internet are actually designed.
Number 4 on our list, scheduling problems. This is all about organizing a list of tasks to get the best possible outcome, which usually means maximizing your profit when you've got deadlines.
So let's talk about job sequencing. You've got a list of jobs to do, and each one has a different profit and a different deadline. So how do you make the most money? The greedy strategy is super clear. You sort the jobs by how much they pay, from highest to lowest. Then you just go down the list and slot each job into the latest possible time you can without missing its deadline. And finally, we have encoding problems. This is basically the magic behind data compression, how we make files smaller so they're way easier to store and send across the internet.
A fantastic example is Huffman coding, which is used in things like zip files. The greedy idea here is pretty clever. You find the two letters in a file that show up the least often, and you combine them. You just keep doing that over and over. This process naturally gives the shortest codes to the letters that appear most often, like E and T in English. It's a simple, greedy choice that dramatically shrinks the file size.
Okay, so we've looked at the theory, we've seen all these classic computer science problems, but here's the best part. You are using these algorithms all the time, probably without even realizing it. Let's see how.
Just picture this super common scenario. You're at an ATM and you need to withdraw, let's say, 2,700 rupees. How does that machine decide which bills to actually give you?
Well, that ATM is running a perfect greedy algorithm. It starts with the biggest bill it can, a 2,000 rupee note. Then it looks at the 700 that's left and gives you the next largest it can, a 500. And finally, for the last 200, it gives you a 200 rupee note. It greedily picks the biggest possible note at each step. And what's the result? You get the smallest number of bills possible.
So we've seen that greedy algorithms are fast, they're simple, and they're often incredibly effective. But remember how we started with that word hoping? Well, that was for a reason. There is a catch, and it's really important to understand where this powerful tool can actually lead you down the wrong path. Let's go back to our knapsack problem for a second. On the left, with the fractional knapsack, you can take bits and pieces of items. So the greedy strategy of just grabbing the highest value per pound, it works perfectly. But now, look at the right side, the 0-1 knapsack. Here, it's all or nothing. You have to take the whole item or leave it. In this case, a greedy approach might grab one big high-value item that almost fills the whole bag. But the true best solution might have been a combination of several smaller items that together are actually worth more. So in this case, that simple best now choice leads to the wrong answer. So at the end of the day, while greedy algorithms are an incredibly powerful and intuitive tool, their magic really only works for problems with just the right kind of structure. So the next time you instantly grab the biggest slice of pizza or you dart into the closest available parking spot, you'll know exactly what kind of algorithm your brain just ran. It's a simple idea, but with some pretty powerful implications.